Hello everyone, welcome to the Kinematics and Dynamics of Machinery course. In this video we're gonna continue the topic that we started before regarding the kinematics analysis of mechanisms. And what we covered so far basically through this course that we discussed and we practiced even how we can do position analysis for different mechanisms. Now we're going to extend the work to consider the velocity and the acceleration analysis. As we discussed before, the kinematics, it means that to fully describe the motion of the mechanism with no, and basically during the study of the kinematics, we don't care about the forces, but we're just interested in describing the motion of the object or like the mechanism that we're already defining or considering. And we basically mentioned that the motion of an object like a mechanism, to be fully described, basically we should do position or displacement, velocity and acceleration analyses. Like you have to define the displacement and how it changes over time or space, and the same thing for the velocity and the acceleration. What we discussed basically using the complex algebraic method, we discussed and we practice how we can do position analysis. Today in this video, I'm going to show you how we can do velocity and acceleration analysis as an extension of the position analysis for the almost the same mechanism that we covered before. So what is the velocity? As you know from physics, that it is a time derivative of a displacement or position vector. And what does it mean, a time derivative? It means that this is the velocity, it is the time rate of position change. It measures how the position or the displacement of an object would change over time. The acceleration as well is the time derivative of the velocity, and it means that this is the time rate of the velocity change, how the velocity of an object would change over time. If there is no change in the velocity of the object, we knew from the dynamic class, from the physics class, that the acceleration should be zero. In case that we do have uniform or constant velocity, it means that intuitively the object has zero acceleration. And this basically what happens when you drive your car, for example, over highways. So, and it means that you barely, in most of the cases, you're going to use the cruise of the car. It means that you are going to fix the speed of the car. In this, at this instant, basically the rate of change of the car is very small or negligible, or it is completely zero. It means that the acceleration that the car is already gaining, it is zero in this case. So what is the general procedure to do a complete kinematic analysis of the mechanism? You just, as you can see, like the first 3 steps are typical, or 4 steps are typically the same one. This is what we did before. Like we basically start by drawing the mechanism and the consider configuration. As I told you, it is advised to draw the mechanism depending on the given angle or the given configuration that you have to solve the mechanism for. As we mentioned that we have a mechanism, so this mechanism basically all the time is moving, and at any instant of time, it has different configurations, it has different positions and different velocity and acceleration of its components. So it is hard for us to solve or do position, velocity and acceleration analyses for the mechanism all over at all the different configurations all the time. It means that we can do it by hand in only one instant of time, 2 instances of time, and so on. If you would like to figure out and like follow the mechanism motion, we can use software to do so, and we can build even the calculation that we are doing over a MATLAB code to end up with a mechanism, and we can see the mechanism how it moves at all instance of time. But basically, since we are solving manually or using by hand, so in this case we can like calculate for only 1 configuration or 2 configurations at maximum, as we practiced the previous meetings. So your objective basically through step 1 here is just to draw the mechanism in the consider configuration, and then you're gonna set up the position vectors over this mechanism. Then you're gonna write the loop-Crusher equation. Then you're gonna carry out the position analysis. These 4 steps, basically, we practiced them, and this is what we discussed before. Following these 4 steps, once you finish the position analysis, What does it mean, position analysis? It means that your objective is just to find the unknowns. And as we agreed, we are limited to only 2 unknowns that we can figure them out using the complex algebraic method. Like these 2 unknowns, it would be the magnitudes of 2 position vectors, the directions of 2 position vectors. It would be magnitude and direction of the same vector, or magnitude and direction of 2 different vectors. These are the 4 cases of the position analysis that we discussed them before. So to figure out or find these unknowns, it means that you already finished the position analysis. Then once we finish the position analysis, it means that all the details in terms of geometry of this configuration, of the given configuration of the mechanism, it is well known. Now we can move to the velocity analysis. So to drive an equation for the velocity analysis, basically, this can be driven by the differentiation of the loop closure equation. We formed a loop closure equation in step 3. So your objective basically is just to differentiate this equation only once with respect to time. This is gonna end up with a velocity equation, or the loop closure equation for the velocity. Because basically we know that if you drive, or if you differentiate the displacement or the position vector, you're going to end up with a velocity vector, and this is what we're going to form. So we're going to form another loop closure equation, but for the velocity, and then we're going to perform almost the same analysis to figure out the unknowns of this loop closure equation. This loop closure equation for the velocity, it will have some given. There are some givens and there are some unknowns. So your objective is just to come up with the unknowns. And again, the unknowns are limited for only 2 unknowns. Then once we solve this loop closure equation for the velocity, it means that we already finished the velocity analysis. Then we're gonna move to the 7th step, which is you are going to differentiate one more time the loop closure equation of the velocity to end up with a loop closure equation, but for the acceleration. So we're gonna differentiate one more time. We're gonna end up with an equation for the acceleration. This equation will include some unknowns. The unknowns are limited for only just 2 unknowns. Solve this loop closure equation of the acceleration. It means that we already finished the acceleration analysis. So this is the general procedure, and I'm pretty sure even in the dynamic class you had a similar procedure. And basically this is normally what we do even from the dynamic class when we do kinematic analysis for different objects or moving mechanisms, as what we're doing here. So this is basically what we're gonna practice doing, especially step 5, 6, 7, 8 through this video. And for sure, we have to do the first 4 steps first for the position analysis. Then we're gonna continue to the velocity and the acceleration analysis. So before we proceed deeply, actually, let us fix some points, some important points here. So we agreed that the position vector we agreed that we are going to represent the position vector as in this form, like r vector as r e power I theta, where r this stands for the magnitude, which stands for the value of this vector. In addition, theta, this is what defines the direction of this position vector, and I, this is the square root of -1, because this indicates that we're already using complex numbers. So that's why the method that we are using here is the complex algebraic method, right? How about if I'd like to, if we can or proceed, basically before we proceed here, if we're gonna look to the r, this r, which is the magnitude of the position vector, it has 2 cases. It would be variable. It would be time variant. It means that it depends on the time, so it would be variable or varying. It would be varying over time. This is an option. And there is another possibility or an option that it would be constant or time invariant. It does not depend on time, right? It's gonna be just constant. The same issue for the direction. The direction, it would be constant, does not depend or varying over time, or it would be variable over time. So why we are defining this one, why we are asking ourselves whatever r is dependent on time or it is constant, time invariant, the same thing for the direction, because we are going to differentiate with respect to the time. So the way that we are going to do the differentiation of this position vector to end up with the velocity, and then we're gonna differentiate one more time to end up with the acceleration. This mainly depend on whatever the r or the theta are variable or constants. Okay, so for example here, based on whatever r or theta are variable or constant, we can define different cases for the derivative to end up with the velocity or the acceleration. So let us discuss these different cases here one by one. So let us consider the case one, that how about in case that we already have the r is variable, is varying with time, and the theta is constant. So let us consider this case that r is variable but theta is constant. A very good example of this case, basically, that you're gonna have a slider that slides over a surface. Whatever this surface is, horizontal surface or vertical surface or even inclined surface, anyway, you'd have a slider that slides over the surface. And we suppose in the position analysis, we have to define a position vector that describes the position of this slider at any instant of time. So if we did derivative of this position vector of the slider, this is gonna give, once with respect to the time, this is gonna give us the velocity vector of the slider. Then if we differentiate one more time, we're gonna end up with the acceleration vector of the same slider. So if we're gonna look to the position vector of the slider, basically, you're gonna find that the r, the magnitude of the displacement change, but the slider is not rotating. It sticks to the surface and it slides over the surface. So what does it mean? It means that in this case, r is variable, is varying over time, it changes over time, but theta is constant. This slide cannot rotate, it can only slide over the surface. And this is a very good example of this case, that you do have r is varying, but the theta angle is constant. So it means that if you decided to describe the position vector of this slider, so r vector, it should be equals r e I theta, as we agreed, right? Now, how about if we would like to come up with the velocity of this one? So this should be the position vector, right? How about the velocity vector of the same slider or the same object? Remember that r is varying, it is a function of time, but theta is constant. So if I ask you to differentiate this equation with respect to time, I do have ei theta, it is a constant, because this exponential term, it is a constant because theta itself is a constant value. So what does it mean? It means that you just gotta consider ei theta as a common factor, and you just gonna do the time derivative just for the r. So you're gonna end up with r dot ei theta. You're just gonna carry on the ei theta as it is. Why? This term is constant, but the r, it will be differentiated with respect to the time. R dot here, r dot, this indicates the time derivative of the position vector r with respect to the time, where you should keep in mind that this r, it should be a function of t, as we mentioned it is variable here, right? So instead of writing dr by dt, just we're gonna save time and just use the r dot as we did even before in the dynamic class. Make sense? So this is gonna give us the velocity vector for this slider. How about the acceleration vector? The acceleration vector is gonna be the same. ei theta, you're just gonna differentiate the velocity one more time. So it's gonna be dv vector by dt. If you differentiate this one with respect to the time, this is gonna give us r double dot. Why r double dot? Because this term is still constant, ei theta. This is gonna give us the acceleration term. Make sense? Where you should understand that the r double dot, it is the second derivative of the time of the position with respect to the time. It is d square r, it is d square r with respect to dt square. This is gonna give us the r double dot. Make sense? So this is simply how we can come up with the velocity vector, the acceleration vector of a position vector. In this position vector has r, the magnitude, its magnitude depends on time, but its direction is constant. And a good example of this case is a slider slides over a surface, whatever horizontal surface, vertical surface, or inclined surface. Make sense? Another aspect here that should be considered is the direction, basically. As you can see that what is the direction of the position? It is theta. Theta, this is just the angle that is specified to define the direction of the position vector. And as you can see that the velocity vector as well still have the same direction as the position vector, like theta also, and there is theta here. How about the acceleration? It is still the direction of the acceleration, it is theta. As we agreed before, all of these quantities are vectors. All of these three quantities are vector. So a vector, it requires magnitude. So the r, this small r, this is the magnitude of the position vector r. And theta, this is the direction of the position vector. How about r dot? R dot, this is v. R dot, this corresponds to v, linear velocity of the slider. This is the sliding velocity of this slider over the ground or over the surface. Okay, so this is the magnitude of the velocity, and theta, this is the direction of this velocity. How about the acceleration? The r double dot, this is an acceleration. R double dot, this is linear acceleration, which describes the acceleration or the rate of change of the velocity of this slider when it slides over this surface. So this is the acceleration, the linear acceleration of the slider. This acceleration, this r double dot, this is the magnitude of the acceleration vector, and theta, this is the direction. So as you can see that all these three vectors, they do have the same direction. So what does it mean? It means that this slider slides with a velocity and acceleration in the same direction as the position vector. They do have the same direction. All the three vectors, all the three physical quantities, the position, acceleration, and velocity for a slider slides over the surface, they do have the same position. Make sense? So this is a good knowledge that we should understand, that for this case, that the r vector, v vector, and the acceleration vector all have the same direction. Make sense? So this is the first case, and this is very simple case. Another case here that would be considered is, how about if we do have the case 2? How about if we do have the r is constant, but in this case we do have theta is varying or variable, varying over time or time dependent. A very good example to this case actually is a link that rotates about a fixed point. Like you do have a link and there is a fixed point that belongs to this link, and this link is just doing rotation in this direction or in the other direction, it doesn't matter. Like we do have here like point A and point B. So if we decided to set up a position vector to this link, so this position vector actually is gonna be r vector equals REI theta, and this is gonna be the position vector. How about the velocity vector here, v vector? So here r is constant, so it's gonna be constant. How about the EI theta? If I ask you to find the derivative of EI theta with respect to the time, so what you're gonna do basically, you're just gonna differentiate the exponential term, which is gonna be the same term times the derivative of the exponent. So it's gonna be EI theta times the derivative of the exponent. What is the derivative of I theta? It should give us I theta dot here. But we have to add here pi over 2 because this is gonna give a shift. Because of the I that founded the exponent, we're gonna end up with a shift in the direction with a 90 degrees. So that's why we are including here theta plus pi over 2. And we agreed before that the theta should be represented in the radian system. Like it shouldn't be in degrees, it should be in radian. So that's why we are adding here pi over 2. So automatically when we do derivative of the EI theta, the exponential term, you're just gonna differentiate, you're just gonna add pi over 2, add 90 degrees, pi over 2 angle to the position that you already have, to the direction theta, then you're gonna multiply times the derivative of theta itself. This is in case that you have theta is varying at this case. So this is gonna give us the velocity vector for this position vector. How about the acceleration vector? The acceleration vector is gonna be the same way. Here r is constant. Then we're gonna have here the differentiation of two multiplied functions. Theta dot, it would be constant, it would be a function of time. Let us consider that it is a function of time at the normal case, right? The conventional case. So it means that there is a derivative of theta dot to be theta double dot, and there is a derivative also to the other term, which is the exponential term, because it includes theta is a function itself. It is a function of time. So it means that this is the derivative of two multiplied functions or time dependence. So what we're gonna do, you're just gonna have fix the first term, then you're gonna multiply times the derivative of the second term. What is the derivative of the exponential term? Again, you're just gonna multiply the derivative of the exponent. What is the derivative of theta? This is gonna give us theta dot, and plus the derivative of pi over 2, which is 0, times the exponential term, which is I theta plus pi over 2. This is the angle. Then you're gonna add over this angle another pi over 2 because you just differentiated another time. You got my point? So the original angle with theta plus over 2, when you differentiate any exponential term, you're just gonna multiply theta dot and you're gonna add over the angle, whatever it is, pi over 2. So the previous angle with theta plus pi over 2, you're gonna add another pi over 2. Make sense? So this is the first term times the derivative of the second term, plus we're gonna switch. Now we're gonna do derivative for the theta to be theta dot to be theta double dot, and we're just gonna carry on the theta plus pi over 2, this term as it is. So we're gonna end up with two terms of the acceleration. So we're gonna say that the acceleration vector at the end is going to be r theta dot square ei theta plus pi over 2, right, plus r theta double dot ei theta plus pi over 2. So this is for the position vector and the acceleration vector and the velocity vector of the case that we do have r of the position vector is constant and theta is variable or dependent on time. And a very good example to this case is a link that rotates about a point. So now so this is for the acceleration. This is the acceleration term. Now let us figure out the directions. So as you can see here, there is difference in the directions, right? The directions won't gonna be the same. So for example, the direction of the position is theta, but the direction of the velocity is gonna be theta plus pi over 2. It means that there is a shift. There is a shift in the phase. There is a shift in the direction between the position vector and the direction of the velocity. How? Basically, as we agreed before, that if we consider that this is the position vector, goes from A to B, this is our vector, right? If I ask you what should be the angle theta, as we agreed, you should come from the start point, draw a line to the right, rotate counterclockwise till you hit the R. This is gonna give us theta. So now, theta, this is the direction of the position vector. How about the direction of the velocity vector? The direction of the velocity vector, it should be perpendicular to the position vector. Why perpendicular? You're gonna add 90 degrees over the theta. So you're gonna have theta, then you're gonna add one more 90 degrees. So what does it mean? It means that the position vector, it will be perpendicular with a 90-degree difference between theta of the position vector and the direction of the velocity itself. Like there should be a 90-degree, and that's why we're already adding here pi over 2. So this should give us the position, the velocity vector, and the velocity vector, it should be goes in the same direction of the rotation, the same direction of omega, because there should be here theta dot, this should be the omega, which is the angular velocity of the rotating link AB. So what does it mean? It means that we already have a shift or a difference between the position of the velocity and the position of the direction of the velocity and the direction of the position vector by pi over 2 that is already shown here. Make sense? How about the acceleration? The acceleration here, it has two terms, not just one term. The first term here, or let us consider the second term. The second term, it's gonna be r times theta double dot. If you remember from the dynamic class that theta dot, this represents omega, angular velocity, but theta double dot, this represents alpha, which is the angular acceleration. Make sense? So that's why here, for example, r theta double dot, this should be like r alpha. And if you remember from the dynamic class, r alpha, this gives the tangential component of an acceleration. We discussed in the dynamic that if we have any object that rotates, any point that belongs to any object that rotates, it has two components of accelerations. One component is the normal acceleration and the second one is the tangential acceleration. So we're gonna say that this should be the tangential component. This should be the tangential component of the acceleration, which it should be equivalent to r alpha that we used to represent the angular acceleration using alpha before. And how about this term? Intuitively, this is gonna be r theta dot. Theta dot, this should be omega. So this is gonna give us r theta dot square, which it should be r omega square. So this should be the normal acceleration. This should be the normal acceleration. This is the normal component of the acceleration. We're gonna give a symbol to this one as a tangential vector, and this one is gonna be a normal vector. Make sense? So this one is equivalent to the r omega square. Okay, so the acceleration has two components. Now if we decided to figure out the directions of these two components, let us see the directions of the two components of the acceleration. So starting with the tangential component, again, it has the same direction as the velocity. It is theta plus pi over 2. It means that there is a 90-degree difference between the direction of the tangential component of the acceleration, or the tangential acceleration, and the position vector. There is a difference with 90 degree, with pi over 2 between theta. What is theta? This is the direction of the position vector. We're gonna shift a 90 degree. This pi over 2 would be added or subtracted, by the way, depending on what? Depending on the direction of alpha. So if we're gonna consider here this direction, and let us assume that this is the direction of rotation of both omega and alpha. What is omega? This is the angular velocity. What is alpha? This is the angular acceleration of this length. If both are rotating in this same direction, so we're gonna have in the same direction as the velocity, we're gonna have another direction that relates to the tangential acceleration, which is at vector. But how about if alpha goes in the opposite direction? And this happens basically in case that this length slows down. It means that there is deceleration, there is decrease in the velocity of the object. So in this case, the direction of the acceleration is going to be opposite to the direction of the angular velocity of this length. So in case that the alpha direction is in the opposite direction, in the other direction, so alpha should go up. It shouldn't be going down. So it means that the direction of the tangential acceleration, it should be perpendicular to the length, in the same perpendicular to the r vector, and it should be in the same direction of its alpha, which is r alpha, this alpha, which is the angular acceleration. How about the normal? The normal, it should be opposite. I messed up here, this should be pi, not pi over 2. There is a mistake here, that this term should be pi. This term, it should be pi, not pi over 2. Why? Because we already have here pi over 2 plus pi over 2. So this is going to give us pi. So if you consider here the direction of the normal acceleration, you're going to find there is a shift by 180 degrees. So what does it mean? It means that if the r goes right, the normal should go left. It means that the normal acceleration all the time, it should be in the opposite direction to the position vector, and this is what we mentioned before in the dynamic class. So what does it mean? It means that the a normal, it should be in the opposite direction. It should go down. If r goes up, so the normal acceleration, it should go in the opposite direction to the position vector. So this should be the a normal. This one, it should be a normal vector. Make sense? So this is how we can define the directions of the velocity and the acceleration in case that we do have a position vector with constant r and varying theta. So this is the second case. So now we discuss the first two cases that we do have r is varying, is dependent on time, but theta is constant. The other case that we do have r is constant, but theta is variable depending on time. How about if we do have both are varying, are dependent on time, right? So this is the most general case. So let us consider this case here. And this is going to be the third case. So in case 3, we're going to have r, both r is varying over time, and we already have theta as well is varying over time. Make sense? A very good example to this case basically is a link and that rotates, for example, and there is a slider over this link. There slides over the link. So the link itself, it rotates. It means that its angle is changing. And the slider itself, it slides. So the r itself is changing as well. So both r and theta are variable. And it's going to be clear as we move through more examples and more demonstration. So what does it mean basically? When you set up the position vectors, you have to figure out which one, which is constant, which is variable in terms of r and theta for all the position vectors. Like in case that you have a slider over a link, automatically you're going to have r and theta both are variable with respect to time. They do depend on the time and change over the time. Because the slider, as I said, it moves, so r will change, and theta also is going to change for this position vector. So the position vector here is going to be r. This is going to be r vector. It's going to be r e I theta. Now let us figure out the velocity vector, v vector. Now we do have two terms, the multiplication of two terms, both are time dependent, right? So the derivative of this multiplication actually is going to be, you're going to fix the first term, then you're going to calculate the derivative of the second term, the exponential term. What is the derivative of exponential term? Simply, you're going to multiply theta dot, and then you're going to add pi over 2 over, or subtract pi over 2 over this angle, plus or minus pi over 2. How about, but basically let us fix it like we all the time adding the plus over 2 to this term. So this is, first of all, we fixed the first term, then we did derivative to the second term. So this is the derivative of the exponential term plus. Now we're going to do derivative to the first term. So r will be r dot, and we're just going to carry on the ei theta term as it is. Make sense? So it means that the velocity of this case is going to be two components. And remember that theta dot indicates omega, angular velocity, but theta double dot indicates alpha, which is angular acceleration. Also remember that r dot represents a linear velocity, but r double dot represents a linear acceleration. Make sense? So this is for the velocity. So now let us figure out these two components of the velocity. So the first term, actually, this is r theta dot. R theta dot, this is like r omega, and this is what we did in the dynamic class. We said that in case that you'd have an object that rotates and there is a point that belongs to this object, and you would like to figure out the linear velocity of this point, is going to be r times omega, right? This is the same expression that we used before. So you're going to say that for now, we're going to say that this velocity, it is a linear velocity due to rotation. This is the linear velocity due to rotation. And we're going to explain this one with more detail. But how about this one? This term, this acceleration, basically it is r dot. It means that this is sliding velocity, this is linear velocity, there is no angular velocity. It means that this is going to be the sliding velocity of the slider. Velocity of the slider itself. And this what explains the slider, because if you're going to give rotation to this link, this slider intuitively is going to be shifted, like it's going to slide over the links. And that's why we say that r is already varying, it's already variable, right? So what does it mean? It means that we do have two components of the velocity, one that describes the sliding velocity of the slider itself, and the second one that depends on the rotation of the link itself. So there is one that is related to the link and there is another one that is related to the slider. But we should keep in mind something here. Let us give some letters or names to this point. If we consider this is like point A and this is point C. So there should be a position vector here. What is this position vector? This should be the position vector between A and C. And it's gonna go from A to C. So this position vector is gonna describe the position of point C with respect to point A. Like you're already standing at A and you observe the position of point and the motion of point C, right? So this point C actually, physically, it's gonna have 2 points. It should be like 2 virtual points. So what does it mean? This point C, I'm talking about the point C, but this point C itself, it is a common point between the slider and the link itself. So basically at this point, there should be 2 points. One point C that is belong to the slider, and there is another point C also that is belong to the link. So that's why we would have 2 components of the velocities. One component, which is this one describes the velocity of point C in assuming that point C is just belong to the link. This component of the velocity describes the velocity of point C assuming that it just belongs to the slider. But physically or actually point C belongs to both. So that's why the overall velocity, this should be the velocity of point C. The overall velocity of point C, it has 2 components. One component that belong in case that the point C belongs to the link. The second one in case that the point belongs to the slider. Make sense? So this term basically, this is known as the sliding velocity, assuming that the point just belongs to the slider. This one is assuming that the point belongs to the link itself. So that's why basically we do have here, if we're gonna look, physically we do have at point C 2 points, not just point. At point C we do have 2 points. Let us give name like C1 and C2. C1, this is the point that belongs to the, let me check my note. This C1, this is the one that belongs to the slider. And C2, this is the point C that belongs to the link. Make sense? So if I ask you, what is the sliding velocity of the slider? Or what is the sliding velocity of point C? So this sliding velocity will be r dot EI theta. Make sense? So this is sliding velocity here. This is sliding velocity will be, we're gonna give it a name as the absolute velocity. This is gonna be the absolute velocity VC1 as a vector. This is the sliding velocity of the slider or the sliding velocity of the virtual point C1 that belongs to the slider. And this velocity actually it is absolute velocity. Why it is absolute velocity? Because this one is defined with respect to point A. It means that this is the sliding velocity or the speed by which point C is going to slide or move over the link with respect to point A. And point A, it is a fixed point, and we said that if you define something with respect to a fixed point, this is going to give us absolute value. So this is the absolute velocity of point C that belongs to the slider, that describe the sliding velocity of the slider over the link with respect to point A. Make sense? How about the other component? So this is one component here. How about the other component of the velocity? This is the linear velocity. This one will be a relative velocity. This is the velocity of point C. This is the velocity of point C with respect to point 2. This is VC1 with respect to C2. It means that here we are describing the velocity of the slider with respect to the velocity of the link, or the linear velocity that comes due to the rotation of the link. Because physically, this velocity, it should be like 2 parts. If we just try to break down the motion of this slider, of this mechanism, or this part, so we're gonna find that this link is gonna rotate first, and the slider will be here. So this is gonna give us like C2. Then what's gonna happen, the slider itself, it will move. Here we are breaking down. physically or in reality, the two motion, they're gonna take place at the same instant of time. It means that the slider is gonna slide and the link will rotate at the same instant of time. But let us break down the motion. It means that first we're gonna have rotation, then we're gonna have a sliding motion. It means that the slider is gonna move to another location like C1. So that's why we would have like two virtual points C1 and C2. And this one, C2, we can find this C2, then we can describe C1 with respect to C2 to end up with the overall velocity of the point C with respect to point A. So this is gonna give us the two parts of the velocity that we observe here, and this is what their physical meaning for the case that you have a slider that slides over a link. Make sense? And if we try to figure out the directions of these two components, you're gonna find that the sliding velocity of the slider, it should be in the same direction. It has the same theta. There is no shift here at the position vector. It means that this slider is gonna slide parallel to in the same direction of the position vector. But this relative velocity basically is gonna be perpendicular to the position vector and is gonna rotate in the same direction of omega. This depends basically on the omega. So for example, if we decided to just represent the directions here for the velocity, so we're gonna have, this is gonna be the position vector, there should be the link, and this is the slider, and we're gonna have here let us assume that this is the position vector, R vector. So for the velocity, basically, we're gonna have two components. One component which is gonna be VC1, this is gonna be the first component, VC1 vector, and it should be in the same direction of the position vector. And let us assume that we do have omega, the angular velocity, or this link rotates in such a way that the angular velocity, it goes in this direction. So we're gonna have another component which it should be the relative velocity as VC1 relative to C2 vector. This should be perpendicular because there is a 90-degree shift. As you can see here, there is a 90-degree shift plus pi over 2, and it should be in the same direction of the omega. Make sense? So these are the directions of the two components and their physical meaning, and this is in case that we do have R is variable and theta is variable. So this is for the position and the velocity. How about this is for the position and the velocity components or vector. How about the acceleration? So now let us move to the acceleration for this case. For the acceleration, basically, we're gonna do one more time derivative. So the acceleration A vector equals, it's gonna be a little bit long. Why? We have two terms, and each one of these two terms is multiplication of different functions. Like the first term, it is the multiplication of three functions. R is variable, theta dot is variable, and the exponential term theta includes theta that is variable. So this is the derivative of three terms. How we can do derivative of three terms? You're gonna fix two and find the derivative of or differentiate the third term and then switch. So you're gonna end up with three terms. This one will be differentiated over two terms. Derivative of the first term, derivative of the second term. So in total, we're gonna end up with 5 terms. How about the derivative of the first term? Let us fix the R and theta dot and do derivative to the exponential term. So we're gonna fix R is constant, or we're just gonna fix R theta dot, then we're gonna do derivative to the exponential term. The derivative of this exponential term gonna give another theta dot, and we're gonna add pi over 2 to the pi over 2 that we already have. So we're gonna end up with pi. So we're gonna end up here with theta dot squared EI theta plus pi, because we already added pi plus pi over 2, so we're gonna end up with pi. Make sense? Plus, so this is the first term. Now, so we fixed R theta dot and we did derivative to the exponential term. Now let us fix R and exponential term and do derivative to theta dot. So we're gonna end up with R, but theta double dot EI theta plus pi over 2. Plus the third term. Now we're gonna fix the theta dot and the exponential, and we're gonna do derivative to the r. So we're gonna end up with r dot theta dot ei theta plus pi over 2. Make sense? So this three term is just for the first term in the velocity vector. The second term is gonna be differentiated over two terms. We're gonna fix r dot one, and we're gonna do derivative to the theta, the exponential term, which is gonna give us theta dot. Then we're gonna add pi over 2 to the theta. So it's gonna be r dot theta dot ei theta plus pi over 2. Plus, then we're gonna fix the exponential term, do derivative to the r dot. So we're gonna end up with r double dot ei theta, and that's it, because we did derivative to the r dot. So we're gonna end up with 5 terms. As you can see, if you just observe this term and this term, these two terms are identical, so we can combine them together, right? So we can end up with another form or a similar form that we're gonna have here: r theta dot square ei theta plus pi plus r theta double dot ei theta plus pi over 2 plus 2r dot theta dot ei theta plus pi over 2. We just sum these two terms together, plus r double dot ei theta. Make sense? So we're gonna end up that the acceleration, it has 4 terms in case that you have both r and theta are variables. So now let us figure out these 4 terms. What does it mean, each one of these terms? Make sense? So starting, keep in mind that, as we mentioned above, that r double dot, it gives us linear acceleration, r dot gives us v, r theta double dot gives us alpha, theta dot gives us omega. So if we started with this term, what should be this term? If you compare this term to the previous case, that you do have theta is variable but r is constant, you're gonna realize that this term gives the normal acceleration. Why? It is r omega square. So this is the normal acceleration. This is a normal vector, which is equivalent to r omega square. And as we agreed before, that the normal acceleration, it should go all opposite to the position vector. It has pi. It means that we are switching the direction. We are moving to the opposite of the theta, which is the position direction. Make sense? How about the second term here? It is r alpha. Theta double dot gives alpha, and this is gonna give us a tangential, as we defined in the dynamics, and even as we defined above in the previous case, for the case that theta is variable, r is constant. So this is gonna give us the tangential component of the acceleration. The acceleration here has 4 components. Make sense? But how about these other 2 components? Coriolis acceleration, which we're gonna give it a symbol like ACR vector, which stands, CR stands for the Coriolis acceleration. How about the Coriolis acceleration and the Coriolis acceleration and the sliding acceleration? The sliding acceleration, it makes sense. We can understand what does it mean, sliding acceleration, that describe how the speed of the sliding motion of the slider over the length would change over time. So this is very simple. This is the sliding acceleration of the slider itself. Okay, but how about these other components? So if we consider C1 and C2, these 2 virtual points again, you're gonna see that this acceleration, basically, this is gonna be the acceleration of C1 vector. This is the acceleration of point C1 that belongs to the slider, and how the speed of the sliding motion of the slider would change over time. But these components, basically, this is gonna be the A normal of point C with respect to point C2. So it should be a relative acceleration that basically depends on the rotation of the link. That's why we already have theta dot, which defines the rotation of the link, right? But this term has no theta dot or theta double dot. So this term of the acceleration does not depend on the rotation of the slider. Yeah, for sure, there is an effect, definitely. But originally, this one is just describe the sliding motion over the link, assuming that the link is fixed, not rotating. But these three terms include theta, or either theta dot or theta double dot. It means that they do depend on the rotation of the length. So that's why these are relative that describe theta C1 with respect to C2. And this is going to be the A tangential of C1 with respect to C2. What are C1 and C2? Again, these are the points, the visual points that we defined above before, in such a way that C2, this is the point that the point C that belong to the link, and C1, this is the point C that belong to the slider itself. Make sense? And we're gonna have here, this is the Coriolis acceleration, ACR C1 relative to C2 vector. It is also kind of relative acceleration. Make sense? So we understand what does it mean normal acceleration, what does it mean the tangential acceleration, and the slider acceleration. How about this one? This basically comes up that depend on the velocity and the linear velocity and the angular velocity of the slide of the link and the slider itself. So it is kind of compound or complex type of acceleration. And basically this type of acceleration exists in different applications, like for example the rotation of the earth itself about its center axis and its in the meanwhile rotation about the sun. This basically generate this kind of acceleration, which is the Coriolis acceleration. So I'm gonna go deeply through the physical meaning of this acceleration basically, but what you should understand that it depends on two main components basically. R dot, which is V, it is a linear velocity, and theta dot, which is omega, which is angular velocity as well. So it depends on both the sliding motion, how easy you gonna give a sliding motion to the slider, and how easy you allow for the rotation of the link, right? So it depends here. And now let us discuss the directions of these four components. So if we're gonna look here to describe the directions, let us consider the position vector R. So starting with the first term here, this one is the normal. It should be opposite to the position vector. So what does it mean? It means that the normal acceleration, it should go down. This is the normal acceleration vector of point C1 with respect to point C2. Make sense? How about the tangential term, the second term? This is the tangential, and that should be normal to the position vector. So it should be pi over 2 plus theta. So it should be normal to the position vector, and it should rotate in the direction of alpha. If this is the direction of alpha, the angular acceleration, so it should go in the same direction of the angular acceleration. So it's gonna be like, it's gonna be a tangential C1 with respect to C2 vector. Make sense? How about the sliding? I skip this one for now. How about the sliding acceleration? The sliding acceleration, it should be in the same direction. It has the same theta. There is no shift. There is no difference here. It is just theta, the same direction as the position. So it should go in the same direction of the position as AC1, where you should understand that AC, this is the sliding acceleration of the slider. Make sense? Now we still need to discuss the Coriolis acceleration and what is its direction. The direction of the Coriolis acceleration basically depends on the direction of the velocity and the angular velocity, the linear velocity and the angular velocity. Why? Because basically it depends on these two components mainly, okay? And this shift, basically, this shift pi over 2, it is added over the direction of the velocity, not over the direction of the position. You got my point? It is different than this, because you already, in this term, for example, we have R, the magnitude of the position. So we're already shifting with respect to the position. Here we're already shifting with respect to the position. But this one, there is R dot. So we are already shifting with respect to R dot. What is R dot? This is V, the sliding velocity of the slider. So the direction of the Coriolis acceleration, it do depend on what? It do depend on the direction of the sliding velocity in addition to the omega itself. For example, in this case, we're gonna say for the normal acceleration, it should be in the opposite. It should be shifted by pi with respect to the position vector, and it do depend on omega squared. This is not a vector quantity. This term, it just, like a scalar quantity. But this term here, it do depend, it should be in the opposite. it should be perpendicular pi over 2 to the position vector and do its direction either up, because for example for this case the tangential, it would be normal or perpendicular to r in either this direction or the opposite direction, right? So which direction you gonna pick? The one that rotates or depend on the alpha. So that's why we do have y alpha, because there is theta double dot, which is alpha. So you decide the direction of the tangential component based on the direction of alpha, which is theta double dot, and it should be normal or perpendicular to the position vector. How about the Coriolis acceleration? It should be normal to the velocity vector, the velocity of the sliding velocity, which velocity r dot, which is the sliding velocity of the slider, and its direction goes up or down depending on what? Depending on theta dot, which is the omega, the angular velocity of this link. So if this is the omega, which is the angular velocity of this link, and from the beginning we specified that VC1 is going up in the same direction here, goes parallel to the position vector. So what does it mean? It means that if this is the direction, if this is VC, let us assume that VC, like we already have VC in this direction, VC1. And this is the direction of omega. So where it should be the direction of the angular acceleration, the Coriolis acceleration. What is the direction of the Coriolis acceleration basically? So if this is the direction of VC1 goes in this direction, your objective is just to try to incline or give a rotation to this VC1 direction in the same direction of omega. Omega goes in this direction, right? In the same direction of omega to be perpendicular, right? So assume that I asking you to rotate this VC1 direction with 90 degrees. So you can give rotation with 90 degrees either into this direction or the opposite direction, right? So if you're gonna give a rotation into this direction, why this direction? Stick to the same direction of omega. So if you rotate in this direction, we're gonna end up with a new direction of VC1. This new direction, it should be the direction of the Coriolis acceleration. C1 relative to C2. Make sense? Let us consider another example in general. How about, for example, if we do have, this is the position vector. Another case, like, forget about this case, and this is point C, and this is point A, and for some reason, we got VC1 goes in this direction, going down, and omega goes in this direction. This is omega. So if I ask you to give rotation, to VC1, so this is the start point, right? So you're gonna give rotation to VC1 either in this direction or this direction, right? Because you're gonna fix the start point and just give rotation to either this direction or this direction. You're just gonna give it rotation in the same direction of omega. This omega rotates in this direction. This direction is counterclockwise direction, right? So you're gonna give a rotation to, so from this point, you're just gonna fix this point and give rotation to VC1 in the same direction of omega. In the same direction of omega, you're just gonna give it, it's gonna rotate in this direction. Make sense? It's gonna rotate in this direction. If to rotate in this direction, so it's gonna take a new direction, which is this one. This new direction automatically is gonna give us the A Coriolis direction of the, or the direction of the Coriolis acceleration. Make sense? Another example here to demonstrate this point. How about if we do have, this is the position vector, and this is point A, and this is point C, and we do have, this is the position vector, and we do have VC for some reason goes up, and we do have omega goes in this direction. So from the start point, again, from the start point of the VC direction, you're just gonna rotate in the same direction given 90 degrees in the same direction as omega. So this omega rotates in this direction. So it will be inclined to this direction. This is going to give us the AR, the ACR, which is the Coriolis acceleration. Make sense? And so on. So this is basically just for now, just to understand these directions. So the objective for now here, we discussed the different cases, 3 cases basically, that depend on either R is constant or variable, the same thing for the theta. These 2 cases, the first 2 cases are very simple. The new thing basically here is the case that you do have both are variables. So we're going to end up with a new term of acceleration, which is known as the Coriolis acceleration, in addition to the sliding acceleration, in addition to the conventional normal and tangential acceleration. This sliding acceleration describes the sliding acceleration, or how the sliding velocity of the sliding is going to change over time. But this normal and tangential, this what describe the acceleration of the point that belongs to the length, which is point C2, and the Coriolis acceleration. This is a special type of acceleration that shows up in just this term. Basically is going to show up under only one condition, that both R and theta are variable, and the direction of this acceleration depends on the direction of VC, which is the sliding velocity of the slider, in addition to the angular velocity of the link itself. Now, before we proceed to some examples on this type of problem, or the velocity and acceleration analysis, since we're gonna form this is gonna be the typical velocity vector. So you're gonna form, this is just for one vector. It means that if you have a loop closure equation, you're gonna have multiple position vectors. What you're gonna do, you're just gonna differentiate every one of these position vector once. So you're gonna end up with a very long equation that include lots of R and theta dot and theta double dot, even for the acceleration. So you're gonna end up with a very long equation for the acceleration. And we have to solve, and we are required to solve these 2 equations, whatever for the velocity and the acceleration, for only 2 unknowns. These 2 unknowns, it would be theta dot, theta double dot, R dot, or R double dot. It depends on the position itself, or the given problem. So, as we did before in the position analysis, we do have a different form, or different form is basically for this exponential term. Here we are differentiating over the exponential term because this is the easiest way. But we agreed before that the position vector that this exponential form of the position vector can be rewritten in a different form. Like we do have R vector. We can write this R vector in a different, like R e I theta. This is one form, and the equivalent one is R cosine theta plus I sine theta, and there should be a parenthesis here, right? So this is the trigonometric form, or the position vector in terms of the trigonometric function. How about if we do have a velocity vector, acceleration vector? In order to solve these equations, we have to separate the real from the imaginary term, as we did in the position analysis, right? So to do so, basically, we have to represent get rid of or replace the exponential term with its equivalent trigonometric functions, right? So for this, basically, you should understand these quantities, or this relation, like the EI theta. We agreed that it's gonna be expanded into the cosine theta plus I sine theta. So if there is R, so you're gonna have R as a common factor outside. Make sense? So this is for the EI theta. For example, how about the EI theta plus pi over 2? Because if you're gonna look up, there are some terms that include theta plus pi over 2, and there are some other terms that include theta plus pi, right? So if there is pi over 2, this is gonna give us definitely the cosine of theta plus pi over 2 plus I sine theta plus pi over 2. Make sense? Typically the same. You just carry on the angle, the cosine the angle plus I sine the angle. How about if we do have EI theta plus pi? So this is gonna give us at the end the cosine of theta plus pi plus I sine of theta plus pi. But the cosine of theta plus pi over 2 or the cosine theta of plus pi, it would be converted somehow into either cosine of theta or the cosine of negative theta or the negative. It means that we can get rid of the pi over 2, right? So how we can do it, basically, you should consider this relation that if you remember this trigonometric relation, and even you can use the calculator and try these relations, like the cosine of theta plus pi over 2, this automatically gives negative sine theta. If you would like to get rid of the pi over 2, this is going to be equivalent to negative sine theta. Also, the sine of theta plus pi over 2, this is equivalent to the cosine theta. It means to get rid of the pi over 2, you're just going to convert it into the cosine theta. Also, the cosine of theta plus pi, this is equivalent to the negative cosine theta, but the sine theta plus pi, it is equivalent to the negative sine theta. Make sense? So just consider these identities when you do analysis, whatever velocity or acceleration analysis for a mechanism. Make sense? So we now actually ready to have an example to give more demonstration and practice. So what I've discussed above here, basically I focus a lot on the directions of these velocity and acceleration, but basically we're gonna consider them a lot. You're gonna find that when I solve the next example, you're gonna find that it is like a systematic procedure. I'm stick to the procedure, do it step by step, so you're gonna end up with everything at the end. It's gonna be much more simple. Okay. Now, let us consider this example to demonstrate the previous steps and the previous demonstration that we discussed before. That we already given this mechanism of two sliders, slider A and slider B, and there is a connecting link between them, AB, as shown here in the figure. And this angle is already given by 30 degrees, 45 degrees, and the link AB has a length of 400 millimeter as already given. And slider B has a uniform velocity of 40 meter per second to the left. It means that it goes to the left in this. This is the direction of the VB. This should be VB direction, okay? And it is given by 40 meter per second, and it is required to find the velocity of slider A, the acceleration of slider A, the omega AB, which is the angular velocity of link AB, and alpha AB, this is the angular acceleration of link AB. To solve this problem, basically, as you can see, all the requirements are either velocity or acceleration, but he didn't ask for any position. So does this mean that can I skip the position analysis? No, you have to stick to the position, start from the position analysis and keep going till the end of the problem. So the first step, basically, as I mentioned, is to quickly draw the mechanism in the given configuration. So this angle here is 30 degrees, this angle is 45 degrees. So it means that this is typically what already given to us here. This is the exact configuration that we have to consider in this problem. So the first step is just to quickly draw this mechanism and basically draw the position vectors mainly. And this is what I'm gonna start with. What I'm gonna do, I'm gonna use the given drawing to represent the position vector. And as we agreed, for any slider, we should set up a position vector, and this position vector, it should go in the same direction of motion of the slider. It should be going over the slider motion. And this slider A, it goes in this direction and moves in this direction. So we're gonna have a position vector, and we agreed that it is better to have this position vector going to the slider. And let us give it this one as 2 vector. Agree? And basically, we're gonna have another position vector, which it should go to the other slider as given here. It should go in this direction. And we're gonna give this one as R1, as position vector 1 that goes to the slider. How about the link? We're gonna have here for this link like slider, like position vector, and we don't care what is the exact position or direction of this link, because this link is already doing general beam motion. There is no fixed point, so let us assume that it's gonna go in this direction R3. But if you switch the direction, no problem. So we're gonna end up with the loop, and the loop here that describe the position vectors, it is closed loop that composed of just 3 position vectors. So let us set up these position vectors here over this detailed drawing here of the mechanism. So we're gonna have, this is gonna be the position vector R2 that moves from point O, let us give a name to this point as point O, to point A, which is slider A, and R1, this is gonna be the position vector for the slider B that moves from point O to point B, and there is R3, which is the third position vector as given here. Make sense? Then before we start forming the loop correlation equation, as we agreed before, we're gonna work here on specifying the givens and the unknowns. What is given, what is unknown in terms of the position vectors R and theta. For each one of these position vectors, there should be an R and there should be theta. So it means that we'd have R1 and 3, and so it means that we should have R1 and we should have theta 1. Let us use theta 1. And as well, we should have R2 and theta 2. The same thing for R3 and theta 3. Make sense? So according to the given information here, what is R1? R1, it should be the distance between point O and point B. Do you think that we do have this distance? No, the only information in terms of distances and magnitudes of position vector is the REB, which is this length is given by 400 millimeter, but nothing else. It means that the R1, it should be unknown. This is first unknown. And theta 1, how much is theta 1? Theta 1, again, it should be, if you draw a line, horizontal line going to the right from the start point of R1 and try to rotate counterclockwise, you won't gonna rotate because you automatically conceded over the R1. It means theta 1, it should be 0 in this case. So we're gonna have 0 for theta 1. Make sense? How about R2? R2, it should be the distance between O to A. Distance from O to A. How long it is not given. It is unknown. So it means that R2 is gonna be unknown. This is the second unknown. So these are the 2 unknowns basically. It means that the rest, theta 2, R3, theta 3 should be given, right? And this is the case. So if I ask you how much is theta 2? Theta 2 basically it should be this angle. If we draw this angle, theta 2 should be from the start point. If you draw a horizontal line going to the right and rotate counterclockwise till you're gonna hit R2, this is gonna give us theta 2. How much is this angle? We have no clue, but we have to calculate it because we already got 2 unknowns before, right? So this angle basically can be calculated at the difference between 45 negative 30. This is gonna give us 15 degrees, right? Because the sum of these 2 angles, theta 2 plus 30, this should give us the 45 degree. It means that theta 2, it should be 15 degrees. So we already got theta 2 by 15 degrees. Theta 2, it is 15 degrees. How about R3? R3 should be the length of the link EB, and there is REB is already given by 400 millimeter. So we already have this one as 400 millimeter. 400 millimeter. If you would like to convert this term into meter, that is fine. If you just keep it millimeter and you're gonna do all the calculations in terms of millimeter, no problem. It's up to you. Anyway, you have to make sure that you have consistent units. How about theta 3? Theta 3, it should be the angle for R3. How much is the angle of R3? Let us figure it out. R3, we start from here, from this point, right? So if we draw a horizontal line going to the right and try to rotate counterclockwise till you're gonna hit the R3 itself, this should give us the theta 3. So how much is theta 3 here? It's gonna be this small angle is gonna be 30 degrees. So if you subtract 30 out of the 360 degrees, we're gonna end up with 330 degrees. This is gonna be the angle for theta 3. So we're gonna end up the angle for theta 3 as 330 degrees. Make sense? Now, once we define these angles, we have to figure out, and these angles and magnitudes, we have to figure out which one is variable, which one is constant. This is a new thing here, right? Because we would like to proceed to the velocity and acceleration, but we weren't gonna ask about the nature or the feature of each one of these position, R1 and direction, whatever it is, variable or constant, in case that we just gonna do position analysis. For the position, we don't care which one is variable, which one is constant, but we do care, and it is important to consider these things for the velocity and acceleration analysis. So how about R1? What do you think of the R1? R1, this should be the position vector, or the magnitude of the position vector R1. What does it mean, the magnitude? This R1, it represents R small one. This represents the distance between point O and point B. Do you think while this mechanism is moving, do you think that the distance between O and B will be constant? Or it's going to change? Definitely it's going to change. After a while, this mechanism is going to have a rotation. This slider is going to move either to the right, slider B is going to move either to the right or the left. It means that the distance between O and B will change. This distance is R1. Since R1 is going to change because of the motion, it means that it should be variable. So this is a variable quantity, that it do depend on time. It has time derivatives. How about theta 1? Theta 1, it should be the angle for the R1. This angle, do you think that there is possibility for R1 vector, for this vector, to rotate? No, it won't gonna rotate. The angle, it is fixed. So we're gonna say that theta 1, it is a constant angle. It is constant angle. But how about the R2? R2, this is the position vector R2, which it should be the distance between O and A. Do you think that the distance between O and A while this mechanism is moving would increase or decrease? Yes. If this slider A slides up, this OA will increase. If it goes down, this OA will decrease, right? So it means that R2, it is variable, it changes because of the motion. It means that it is time dependent, so it should be considered as variable. But how about theta 2? Just right. It is better to write next to each one to know exactly which one is variable, which one is constant, because you're going to need this information in the velocity and acceleration analysis. How about theta 2? Do you think that theta 2 would change? Theta 2 should be the angle for the R2. This angle won't going to change. While this mechanism is moving, this line will not rotate, this line also will not rotate. So theta 2 is confined between two fixed lines that they are not rotating. So it means that theta 2, it is a constant in this case. So theta 2, it is constant. How about R3? R3, it should be this distance between A and B. This distance between A and B, this represents the length of a physical length that is already there. And this length won't gonna change its length. It's just gonna rotate, but it won't gonna, its length, it is fixed. It won't gonna rotate. It would gonna change. It means that R3 is already constant. But how about theta 3? Theta 3, this is the angle for the length 3, which is for the length EB, and this theta 3 definitely is going to change. Why it's going to change? Because this length EB will rotate. As the slider A, for example, moves down and slider B moves right, so you're gonna find a rotation. This length AB will change, will rotate, and the angles even 30 and 45 degrees will change. So what does it mean? It means that theta 3 itself is going to change because the length itself rotates. Theta 3, this is the theta for the length with the position R3. It means that the R3 is going to, theta 3 is going to change, so it's going to be variable. So here we end up, we defined which one of these quantities, R's and thetas, which one is variable, which one is constant, and this is a new thing. Then you're going to proceed to the position analysis typically the same way like what we did many times before. So we're going to start here. The step 1 is just position analysis. So what we basically do in the position analysis, the first step is just to form the loop closure equation. Loop closure equation, it depends on the rotation of these position vector. With a free position vector, you're gonna see that R2 goes in the same direction or rotates the same following the R3, but R1 in the opposite direction. So the loop closure equation in this case is gonna be R2 vector. In the same direction there is R3, so it's gonna be plus R3 vector. But in the opposite direction we do have R1 vector. Make sense? R2 has one unknown, which is the position, but the direction is the one unknown, which is the magnitude, but the direction is known for R2. R3, as shown down here, it is fully defined in terms of magnitude and direction. So R3, it is fully defined. But R1, it has unknown, which is the magnitude, but the direction is already known. Make sense? Then what next? Basically, if you're gonna look to this case, this is which case? This is it case 1 or case 2 or case 3? So this is case 2. Why case 2? Because we do have two unknowns. These two unknowns are the magnitudes of two different positions. So this is typically case 2 of the position analysis. Then what we're gonna do basically is sticking to the procedure. What you're gonna do, just represent this, each one of these are represented in terms of its exponential form. So we're gonna have here R2. We're gonna have R2 EI theta 2 plus R3 EI theta 3 equals R1 EI theta 1. Before you proceed, basically, what I'm going to tell you is, in case that there is any one of the thetas, any one of these thetas, either theta 1, theta 2, or theta 3, that has a value of either 0 degree or 90 degree, 180 degrees, or 270 degrees, it means that this common angles. And the other condition is that the angle should be constant. It shouldn't be variable. In case, so again, in case that you have one of these angles, theta 1, theta 2, theta 3, is with 0 value, or 90 value, or 180 value, or 3 or 270 value as the angle. In addition, the angle is constant, not a variable. In this case, you can directly substitute with its value. It is better. It's gonna save some time in terms of calculation and make the calculation more easy in case that you substituted with its value directly into this instant at this step. Like the case, this applies to only to theta 1. Theta 1 is already 0 and it is constant. So that is fine to substitute for theta 1 here equals 0. But theta 2, don't substitute for theta 2. It is constant, yes. But theta 2 equals 15 degrees. This one even if you substitute, it's gonna make the calculation and the writing more complex. But the same thing for theta 3. Theta 3, even if theta 3 is 0 or 90 or 180, don't substitute with its value. Why? It is variable. Make sense? So the only angle that you're gonna substitute with its value at this step is the angle with 0 degree, 90 degree, 180 degree, 270 degree, and the second condition that it should be constant. Make sense? And this applies only to equation 1. So what I'm gonna do basically, to theta 1. So what I'm gonna do, I'm just gonna rewrite again this equation, but for theta 1 equals 0. For theta 1 equals 0, this term will be definitely e bar 0 will be just 1, so this is going to give us R1. So it means that we're going to end up with R2 EI theta 2 plus R3 EI theta 3 equals R1, and we're going to give a number to this equation like equation 1. So this is the loop closure equation in the exponential form. And we need this form. Why? Because this is the equation that we are going to differentiate to come up with the velocity equation. And if we differentiate one more time, we're going to come up with the acceleration equation. Make sense? So this equation is a big deal to us, which is the equation 1. Then stick to the procedure of case 2. For case 2, the procedure directly just decompose these terms into their exponential trigonometric function, cosine and sine. Then we're going to convert them into real and imaginary parts. So if we decompose this equation directly into its real and imaginary parts, we're gonna end up that this term will be cosine theta 2 plus I sine theta 2 as we discussed before. So it's gonna be automatically R2 2 cosine theta 2, this is the real, just collect the real terms, plus R3 cosine theta 3 equals R1 is already real. And this is going to give us equation A. And the imaginary part, the imaginary term, is going to be R2 sine theta 2 plus R3 sine theta 3 equals 0, because there is no imaginary term here, and this is going to give us equation B. From equation B directly we can find one of the unknowns. If you're going to look to the unknowns here, so to the values, R1 is unknown. R1 is unknown. It is unknown, but theta 3 we already have this, its value by 330 degrees. R3 we already have it by 400 millimeter. Theta 2 it is already 15 degrees. R2 is already unknown, so this is the second unknown. But here we'd have only, so in the first equation we'd have two unknowns, but in the second equation we'd have only one unknown. Theta 2 is already 15 degrees, theta 3 is already 330 degrees, but R3 it is 400 millimeters. So if we solve directly equation B, we can find R2. So automatically from equation B, we're gonna end up that R2, we can solve for R2. We're gonna find R2 equals 772.74 millimeter. Just do the calculations, solve one equation and one unknown, you're gonna find R2. Once you find R2, substitute into equation A to find the other unknown, which is R1. Is going to be very simple equation. You're going to find R1 will be obtained by 347.37 millimeter, and this is very simple problem in terms of position analysis. Make sense? So we finished the position analysis as we did many times before. Now let us move to the next step, which is the second step, velocity analysis, and this is the new thing, the velocity analysis. Also, it is very simple. You start, you just gonna choose again this equation 1. You're gonna start from equation 1. Okay? So there should be, this should be equation 1, right? This should be equation 1. So what we're gonna do basically, we are going to differentiate equation 1. So to differentiate this equation, you should consider which one is variable, which one is constant, right? According to the thing that you specified above here. So let us consider here, how about R2? R2 it is variable. So R2 it is variable. So we're just gonna give a symbol like V to indicate that this is variable. The theta 2 it is constant. So theta 2 it is constant. So it's gonna be C. R3 it is constant, but theta 3 it is variable. R1 it is variable. R1 is already variable. Make sense? So if I ask you what is the derivative, now we are going to differentiate term by term, starting with the first term, which is R2 EI theta 2. So what should be the derivative of the first term? It is the derivative of two terms, but the first term is variable, but the second term it is constant. The direction is constant, the magnitude is variable. So the derivative of this term will give us R2 dot EI theta 2 will not be differentiated. Make sense? But how about the second term? The second term will be plus. R3 is constant, but theta 3 is variable. So it's going to be R3 is constant. The derivative of the exponential term, as we mentioned, you're going to have theta dot EI theta plus pi over 2. You're just going to add pi over 2 to the angle. But this theta is theta 3, and this theta is theta 3. So we're going to end up with R3 theta 3 dot EI theta 3 plus pi over 2 equals R1 is variable. So it's going to be R1 dot. This is going to give us the second equation. This second equation, this is the velocity equation, and this equation that shall be differentiated again to end up to find or to come up with the acceleration equation for the acceleration analysis. It means that this equation we're going to use it for the acceleration analysis. Make sense? Before we proceed in solving this equation, we have new variable that came up here, r1 dot, theta 3 dot, and r2 dot. Make sense? So we have to understand which one of these variables is already given, which one is unknown to do velocity analysis. Typically the same what we did for the position analysis. So on a side here, we do have three new variables, which are the r1 dot, and we do have the r2 dot, and we do have the theta 3 dot. Make sense? R dot indicates V. R dot indicates V. So what does it mean? What is R1? This should be the sliding velocity of slider B. R1, it should be the sliding velocity. This is the rate of a change of the position R1, which is the speed over R1. The speed over R1, it belongs to the slider. So if we're going to talk about R1 dot, it means that we are talking about the sliding velocity of the slider itself. The sliding velocity of the slider B is already given here by 40 meters per second. So it is already given by 40 meters per second, and the direction of this sliding velocity of slider B is already going to the left. So the value is 40 and going to the left. So what does it mean? The R1 dot, the R1 small dot, it is equals to 40 meters per second. So the value it is 40 meter per second, and it should go to the left. Going to the left, we're gonna add here a negative sign. Why we are going to add this negative sign here? I'm adding this negative sign because the direction of the sliding velocity, which is the 40 meter per second, it is opposite to the R1. This VB is already given. This is the direction of the sliding velocity as it was given. But I considered R1 we considered R1 in a direction that is opposite to VB. So VB, it is opposite to the R1, so that's why I'm including this negative sign down. So this negative indicates that the direction of the sliding velocity, it is opposite to the assumed direction of R1, which is the position vector that you considered before. Make sense? So what I'm gonna do here, so that's why we already included here 40 millimeter, and we included the negative here next to the 40 millimeter. So R1, it should be negative 40 meter per second. How about R2 dot? R2 dot, it should be the sliding velocity of slider A, because this is the rate of change of the position R2, the position vector R2. So this R dot, it should be V. V, it means that this should be the sliding velocity of slider A. Do I have the sliding velocity of slider A? Is it given? No, it is not, and it is already required. So what does it mean? It means that R2 dot is unknown. And remember that we are allowed for just only two unknowns for the velocity analysis. So intuitively, theta 3 it should be unknown. This is the second variable. Theta dot, it is omega. This is angular velocity, right? So theta 3 dot, it should be the angular velocity that belongs to the R3, and R3, this represents the position vector of the length AB. It means that this should be the angular velocity of the length AB, which is not given. This angular velocity of length AB, it is not given, but it is required. So what does it mean? It means theta 3 dot, it should be unknown. So that's why we end up with only two unknowns. It means that we can do velocity analysis to come up or find values of these two unknowns. This is the meaning of velocity analysis. Typically the same like the position analysis. But in the position analysis, we consider four cases. These four cases depended on what is the type of the unknown. Is it direction or magnitude? Are the two unknowns belong to the same vector or different vectors? So we had four cases, but for the velocity of the acceleration analysis, there is no cases. The equation, it will be simply directly solved. You're just gonna decompose this loop closure equation into real and imaginary parts. So you're gonna end up with two equations, solve them, and the two unknowns will be solved. It means there is no cases like the position analysis or like what we did before in the position analysis. So the velocity analysis, it means that you are required to solve this equation. It will be easily solved. So to proceed for the velocity analysis, basically, what I'm gonna do, directly decompose this equation into, or rewrite again this loop closure equation in terms of the trigonometric function cosine and sine. So if we wrote this equation in terms of cosine and sine here, so we're gonna have R2 dot cosine theta 2 plus I sine theta 2. This is the trigonometric function, or the cosine and sine form of this first term. Make sense? How about the second term? It's gonna be the same, plus R3 theta 3 dot. This is a common factor, and the exponential term will be expanded into the cosine theta 3 plus pi over 2 plus I sine theta 3 plus pi over 2, and that's it. So this is the second term. How about the third term? There is no need, it's just R1 dot. Very simple. Then your objective is just to decompose this one into real parts and imaginary parts. So what is the real part here? The real part is going to be R2 dot cosine theta 2 plus R3 theta 3 dot. This is imaginary part, so it will not be included in the real part. Then I'm going to move to the second term. I do have only the cosine as real part, so it's going to be the cosine of theta 3 plus pi over 2. This is an imaginary part, it has I, equals R1 dot is already real. So this is going to give us equation A. Then I'm going to move to the imaginary part. The imaginary part is going to take the other side, which is the sine. So it's going to be R dot sine theta 2 plus R3 theta 3 dot sine theta 3 plus pi over 2 equals 0. There is no imaginary part on the right side, and this is going to give us the second equation. So we end up with two equations. These two equations has only two unknowns. Very simple. Two equations, two algebraic equations even. You aren't gonna find angles like what we did in the position analysis. These two linear algebraic equations that can be easily solved even using the calculator, okay, or by elimination. So, but you have to consider some identities for the trigonometric functions here that we mentioned them before, that you should consider that the cosine of theta 3 plus pi over 2, just to make the calculation more simple, it should equal to the negative sine theta 3. So it means that to get rid of this pi, you're just gonna replace this term with a negative sine theta 3. And the same thing for the sine term, the sine of theta 3 plus pi over 2, it should equal to the cosine theta 3. So what does it mean? I can rewrite these two equations one more time, but without this pi over 2 to make the calculation more simple. So we're going to end up here with R2 dot the cosine of theta 2, then the cosine theta 3 plus pi over 2, this gives negative sine theta 3. So we're going to have here negative R3 sine theta 3 dot sine theta 3 equals R1 dot, and this is going to give us the first equation as equation 1 dash, for example, just to distinguish between this equation and the previous one. Then we're going to have another equation which is R2 dot sine theta 2, and the sine theta 3 plus pi over 2 gives positive, so it's going to be plus R3 sine theta 3 dot cosine theta 3 equals 0, and this is going to give us the second equation B dash. Then we end up with two equations in just two unknowns. What are the unknowns? Let us substitute with the values here. How much is R2 dot? R2 dot, it is unknown. So this is one of the unknowns. It is unknown. Theta 2, if you remember, it is above. We got it. It is already given by 15 degrees. So we already have theta 2 by 15 degrees. And R3 is already... we already got it. All the R's, all the thetas, we already got them. R3 is already given by 400 millimeter, theta 2 15 millimeter, theta 3 330 degrees. So what does it mean? R3 is already given by 400 millimeter. Theta 3 dot, it is unknown. Here we are talking about theta 3 dot, but theta 3 itself, the angle itself, it is already given by 330 degrees. R1 dot, it is given by negative 40,000. Take care of this value. It is negative 40,000. R1 dot, it is negative 40 meter per second, but we're still working in millimeter, so this value should be negative 40,000 millimeter per second. Make sense? So you're gonna substitute for R1 here. R1, it should be the negative 4,000 millimeter per second. Make sense? And why we are including this negative? Because it goes in the opposite direction to the R1. How about the second equation? The same. R2 is unknown. Theta 2 is already given by 15 degrees. R3, it is 400. Theta 3, it is unknown. And theta 3, it is given by 330 degrees. And the right side is just 0. So solve two equations in two unknowns that should be solved. You can solve them by elimination, like this case. For example, I can say from equation B dash, we can just find R2 dot in terms of theta 3. So solve for R2 dot, we're gonna find R2 dot in terms of theta 3 will be negative 1338.42 theta 3. Then we're gonna substitute into this relation, into equation A dash. If we substitute into equation A dash, this is gonna give us, substitute into equation A dash, this is gonna give us this relation, like theta 3. So we're gonna end up with one equation and just one unknown, and this unknown will be theta 3 dot. This should be theta 3 dot, by the way. So this is gonna give us theta 3 dot, which it should be omega 3, which it should be the omega of length EB. This is the required angular velocity of length EB, as we mentioned, and this will be obtained by solving equation, by substituting this equation into A1 dash and A dash. Then we're gonna end up with one equation in just theta 3 dot, simple, very simple algebraic equation. We're gonna end up with 36.6 radian per second. Why radian per second? Because it is angular velocity, and this is one of the requirements. And as you can see here, it is positive value. Positive, it means that the direction of this omega 3, it is counterclockwise direction. So if the omega that you're gonna get from the calculation, you find that its value is positive, this indicates that the direction of the angular velocity, it is counterclockwise. This is the positive direction. If it is negative, so it means that it is in the clockwise direction. Why the positive is counterclockwise, the negative it is clockwise? Because from the beginning we specified the angle that we was rotating in the counterclockwise direction to have a positive theta. So it means that from the beginning we assume that the counterclockwise direction is a positive and the clockwise direction is a negative. So that's why in case that we got the omega or the theta dot, any theta dot, whatever it is, positive, it means that the direction of this angular velocity, it is counterclockwise direction. Once we find theta 3, you can substitute into this expression to come up with the value for R2. We didn't finish the velocity analysis yet. We just, to finish, it means that you have to find all the two unknowns. We have two unknowns, we got only theta 3 dot, we still working on R2 dot. So R2 dot, it means that substituting to this expression, we're gonna find R2 will be obtained by negative 48.989 meter per second. I did the calculation, then I converted into meter per second. So what does it mean, this negative? This negative indicates that it goes opposite to its vector. What is position vector? Its position vector, this is R2 dot, this is V2, this is the sliding velocity of the slider over R2. It means that this direction of this velocity, it is opposite to the R2 vector direction. Make sense? Why? It is negative. But if it is positive, it means that it goes in the same direction of the R2. Make sense? So this is for the velocity analysis, and these are the two unknowns. Velocity analysis, it means to find the two unknowns. How about the acceleration analysis? We're just gonna stick to the procedure to repeat again. So for the acceleration analysis, So now let us move to the acceleration analysis, and I've brought here the equation 2, which was the velocity loop closure equation that we got in the velocity analysis, because this is the equation that we have to differentiate right now. So we are going to do derivative to this equation, and you should keep in mind which are the variable, which are the constants, right? We do have here, in addition to the r and to the position vectors like r and theta, in addition to these r and theta, we do have r dot and theta dot. R dot, this is the velocity, the linear velocity, and theta dot, it is a variable, this is an angular velocity, and even these r dot and theta dot themselves would be variable or constants. So for example, going back here to the velocity analysis, we do have three variables that include dot basically, right? Which one of these parameters, r dot, r1 dot, r2 dot, theta 3 dot, that would be constant or variable? This r dot would be constant or variable does not depend on r1 itself would be constant or variable. For example, you may have r1 itself is constant, or no, forget about it. It means that r1 it should be variable anyway, but if r1 is variable, r1 dot it would be variable or constant. R1 dot, this indicates the sliding velocity of the slider B. This is the sliding velocity of the slider B. And as mentioned here, it was mentioned that slider B has a uniform velocity. What does it mean, a uniform velocity? It means that the sliding velocity of the slider B, it is constant. It is uniform. So what does it mean it is constant? It means that r1 dot it is constant. It means that r1 double dot will be 0. There is no derivative for a constant value. Make sense? So that's why it is important to keep eye on the information that is going to be given to the velocities in the given problem. Make sense? Here it is mentioned that we do have uniform velocity of 40 meters per second to the left. It means that the sliding velocity, which is VB, which is R1 dot, it should be constant here. So this R1 dot, it should be constant. So you can add C next to it, indicating that this is constant. But how about R2 dot, theta 3 dot? I have no clue. I don't know whatever it is, constant, it is variable, I don't know. This, for example, for R1 dot to be constant, this not necessarily make the R2 dot or the theta 3 dot to be constant as well. Make sense? So it means that if the velocity is already given and he mentioned directly that the velocity is constant or uniform, this indicates that the R dot will or the theta dot will be constant. Other than that, especially if it is unknown, like the case of R2 dot and theta 3 dot, so in this case we have no clue, and it means that we're gonna deal with this one like variables. And this is what we're gonna consider when we do the acceleration analysis. So for example here, if we're gonna consider these points, we said that R2, it should be variable. We're gonna deal with this one like variable. Theta 2 from the beginning, it was constant. From the position analysis, theta 2 was constant, but theta 3 was variable, right? Here, theta 3 is constant, theta 3 is variable. R3 is constant, right? So we're gonna consider these. It means that R3 is constant. Theta 3 dot, it is variable. We have no clue whether it is variable or not, so we're gonna consider it variable. Theta 3 is already variable, and R1 dot, it is constant. As we mentioned, R1 dot, it was constant here, right? And theta 3 was variable. Theta 3 was variable, R3 was constant, theta 2 was constant, right? So we're gonna consider these things here when we do the derivative for the position analysis. So for the position analysis, let us do the derivative for the first term. It is very simple. The exponential term is constant, but the r dot, it is variable. So the derivative will gonna give us r2 double dot and ei theta dot. We just gonna carry on this term as it is. Plus, how about the R3? The R3, we said that the R3, it is constant. The R3, it is constant here. The R3, it is constant. So we're gonna have here for this term, we're gonna have the derivative of the three terms of the multiplication of three variables but this first variable is time independent, so it is just constant. So we're gonna have R3 as a common factor here, R3 as a common factor. Then we're gonna open the square bracket. Then we're gonna do the derivative of the multiplication of two functions, theta 3 dot and the exponential term. So we're gonna fix the first term, which is the theta 3 dot. Then the derivative of this term, this is gonna give us another theta 3 dot, so it will be squared EI theta 3. Then we're gonna add to the pi over 2 another pi over 2, so this is gonna give us pi here. Make sense? Plus the theta 3 will be double dot, because we're gonna integrate this, differentiate this term, and we're just gonna carry on the exponential term at theta 3 plus pi over 2, and we're gonna close the square bracket. So this is the derivative of the second term equal. The derivative of this term, it should be 0. Why? It is a constant term. He mentioned that this R double dot, it is constant. So this is gonna give us the third equation, which it should be the acceleration equation. But basically, we won't gonna do anything further with this equation, right? Except we're just gonna decompose it into, rewrite this equation again into the trigonometric form, just to do the find the unknowns of the acceleration terms. But if you're gonna look here on the side here, we do have some terms that include double dot, like R2. We do have R2 double dot, and we do have theta 3 double dot. R2 double dot, this indicates acceleration. This indicates the acceleration of what? Of R2. What is R2? This is the position vector that describes the motion of the slider A. So R2, this belongs to the slider A. It means that R2 double dot, this is the sliding velocity of slider A. Do you have this sliding acceleration of slider A? Do you have the sliding acceleration of slider A? No. So it means that R2 double dot, it is unknown. So R2 double dot, it is unknown here. So this is one of the unknowns. And intuitively, we're going to have theta 3 double dot is unknown, because in the acceleration analysis, we are allowed for only just two unknowns, right? Theta 3 double dot, this is theta double dot, this is alpha, angular acceleration. Alpha of length 3, or for the R3 that belong to the R3, and R3, this is the length EB. It means that alpha, this should be the alpha EB, which is theta 3 double dot. And also it is unknown, it is required. So if it means that if we find this unknown, we already got everything. So then what we're gonna do, we're gonna rewrite again these terms into their exponential cosine and sine terms. So we're gonna have R2 double dot, then we're gonna open the parentheses cosine theta 2 plus I sine theta 2 plus R3. Then we're gonna have the square bracket here, or just multiply R3 times theta 3 dot square. Then we're gonna have the cosine of theta 3 plus pi plus I sine theta 3 plus pi. So this is the first term, plus the second term, which is gonna be R3 times theta 3 double dot. So R3 theta 3 double dot, the cosine of theta 3 plus pi over 2 plus I sine the theta 3 plus pi over 2, and this is going to give us the second term equals 0. Then what we're going to do, we're going to decompose this equation into its real and imaginary parts. So we're going to have here the real part. The real part is going to take the R2 double dot, the cosine of theta 2, plus R3 theta 3 dot square. We do have here cosine theta 3 pi. Cosine theta 3 pi, this gives the cosine theta plus pi. The cosine theta plus pi, this gives negative cosine theta. This gives negative cosine theta. Like this term, very quick here, we do have theta plus pi. So this term will be negative cosine theta 3. And to get rid of this pi here, the sine theta plus pi gives also negative sine theta 3. But the sine theta plus pi over 2, this gives the cosine of theta 3, and the cosine theta 3 plus pi over 2, this is going to give us the negative sine theta 3. Make sense? Just consider these changes to get rid of the pi or the pi over 2 and carry on. So we're going to have here R3 theta 3 dot square the first term here. We are collecting the real term, which it should be this term, so it's gonna be the negative. It means that this term should be negative here. It means that we're gonna have negative the cosine theta 3. Then there is no imaginary term. Then here we're gonna consider negative r3 theta 3 double dot sine theta 3, which it should be this term. Then forget about the imaginary equals 0. This is gonna give us equation A, the real part. Then how about the imaginary part? It's gonna be the same, r2 double dot the sine theta 2. We're gonna consider just the sine. The imaginary part here, we're gonna have the negative r3 theta 3 dot square times sine theta 3. So it's gonna be sine theta 3 because we already considered the negative outside here. Then we're gonna have the plus of r3 theta 3 double dot the cosine of theta 3 equals 0, and this is gonna give us the second equation, equation B. Make sense? So we got the real and imaginary. Our objective right now is just to substitute as we did many times before. How much is r2 double dot? We have no clue. This is unknown. Theta 2 is 15 degrees. Theta 3 dot square. Theta 3 dot, we already got it in the velocity analysis. Theta 3 dot, we got it by 36.6. So it is 36.6, but it should be squared here. How about R3? R3, it is 400 millimeter. It is already given, 400. And theta 3 is already given by 33 degrees. This should be 400. And theta 3 double dot, this is the unknown, one of the unknowns. And theta 3 is 330 degrees. Make sense? So as you can see in the first equation, in equation A, we do have two unknowns, which are R2 double dot and theta 3 double dot. How about the second equation? We're gonna find the same two unknowns. We do have here, this is unknown. Theta 2 is already 15 degrees. R3 it is 400. And theta 3 double dot, it is 36.6 degrees radian per second. And theta 3 is already 330 degrees. And this should be 400. This should be unknown. This is the second unknown. And we do have 330 degrees. Then we do have two unknowns in just two equations in two unknowns. So simply, if you try to solve these equations, we're gonna end up that from equation A or equation B. Let us start from equation B. We can end up that R2 double dot is gonna be obtained by negative 1035 132.48 negative 1338.4 theta 3 double dot. Then we are going to substitute this expression into equation A. Substitute into equation A and solve for the result. This is gonna give us the theta 3 double dot at the end, which it should be alpha 3, which it should be the alpha AB for length EB. We're gonna get it by the negative 1339.56 radian per second square. Why radian per second? Because it is acceleration. Radian per second square. What does it mean? It is negative. Negative, it means that the correct direction of this angular acceleration is clockwise. And it rotates in the clockwise direction. What is alpha AB? This is the angular acceleration of the length AB, and this is one of the requirements. Then how about the R2 double dot? This should be the acceleration of the slider A. This should be the acceleration of the slider A, which is going to be obtained by 757.776 meter per second square. It means, and it is positive. So what does it mean positive? It means that it is in the same direction, to the R2, in the same direction as R2 vector. Okay. So these are the requirements. It was required to find the acceleration of slider A, the angular acceleration of the length EB, in addition to the angular velocity and the velocity of the slider A and angular velocity of the length AB. How about So now we've finished. How about if we would like to add the directions of all of the velocities and the acceleration of all of the points that we have here? Like for example, how about R1, the directions of the different velocity components of the R1 vector that correspond to the R1 vector, to the R2 vector, to the R3 vector. Okay, we can do it, we can add these directions. So let us start first with the velocity components, and let us record the equation number 2 for the loop closure equation for the velocity analysis that we got. It was in the form like R2 dot, I'm just gonna write the equation here, EI theta 2 plus R3 plus R3 theta 3 dot EI theta 3 plus pi over 2 equals R1 dot. This was the equation 2 for the velocity analysis, and from this equation we're gonna come up with the directions of the different components. Starting with the first term that we have here, it is R2 dot EI theta dot. This term, basically this term, R dot, it should be V2, so R dot do, it should be V2. V2, this should be sliding, this should be like a sliding velocity, linear velocity along R2, which since we have a slider, it means that this should be the sliding velocity of the slider A. Okay, so what is the direction of V2? V2 here, according to this term, it should be the same direction of R2, but it should be the same direction wherever it is parallel in the same direction or in the opposite direction. It means that we may add here plus a pi, which is gonna be the same value, the same value but opposite direction. So in case that especially in case that we do have V2 sliding velocity like this case, and there is it should be parallel. Theta 2 here, it means that it should be parallel to the R2, but it is parallel, it means that it is not necessary to be in the same direction or in opposite direction to the R2 that you assume. This basically depends on the concept, because the velocity, even the acceleration, they would have different directions because of their physical term, or this physical meaning is different than the position, different than the acceleration. Anyway, V2, which it should be R2 dot, you have to check your answer down here. We got R2, you have to check whatever it is positive or negative. We got it negative. It means that it should goes in this opposite direction to the R2 direction. So the direction of the R2, which it should be V2, which it should be VA. This should be the sliding velocity of slider A. So it should goes opposite to the R2, but parallel, because it has the same direction in terms of theta 2. So it's gonna be VA vector. This is the direction of the sliding velocity of the slider A. So this is for the first term. How about this term? Let us move the R dot, because it is very similar. R dot just should be the sliding velocity of the slider B, and the sliding velocity of the slider B is already given by 40 meters per second, right, and goes to the left, and that's why we substitute for this R1 down by negative 40, because it is opposite to the R1 that we assumed. Make sense? So it means that this 40 meters per second should goes to the left in this direction. But how about this term? This term, it should be theta 3 plus pi over 2. It means that it should be perpendicular to the R3 vector. So it should be perpendicular to the R3. This is the R3 vector. So we do have a velocity which is a linear velocity that should be perpendicular to the R3 vector. But the perpendicular, is it gonna go up or down? This depends basically on the direction of theta 3 dot. The direction of theta 3 dot, which is omega EB that we got. This should be omega EB, right? Theta 3 dot, we got it down. So this should be, by the way, this V, it should be V3 for length 3, for the length EB, which it should be like the relative velocity of point B with respect to A, or A with respect to B. It means that it is the relative velocity or the linear velocity that belongs to the length 3 vector. Make sense? So what is the direction of theta 3? Theta 3 dot, we already got it here, positive. It means that it should be in the counterclockwise direction. So it means that in the mechanism, theta 3 which it should be omega AB, it should rotate counterclockwise direction, so it should rotate in this direction. This should be omega AB, or which it should be the theta 3 dot. So what does it mean? It means that according to this direction of the R3, the direction of this relative velocity, it should be, which it should V3 vector, it should be perpendicular to the R3 and rotate with the same direction as omega AB, which is theta 3 dot. Make sense? So these are the directions, the three directions of the velocity component that we already got in this case. Make sense? Let us do the same for the acceleration. So for the acceleration, I've brought this equation, which is the third equation, equation 3, that we use for the acceleration analysis. And you're going to find here three terms. This is the first term, second term, third term. This first term that just belong, would have only one term that belong to R2, the position vector R2. This term, it has R2 double dot. So R double dot, this indicates acceleration, linear acceleration A. And this belongs to R2. It means that this should be the sliding acceleration of the slider A. And so this R2, it should stand for the acceleration of slider A. And the acceleration vector of the slider A, it should be parallel to theta 2. It should be parallel to R2, but it would be opposite or in the same direction or in opposite direction. But anyway, it would be considered parallel to R2. So from the acceleration analysis, we already got R2 double dot. We got R2 double dot with positive value. It means that it should be in the same direction as R2. So it means that it should go in the same direction as R2. So this should be the direction of the acceleration of slider A. So this should be the acceleration of slider A. It should be parallel in the same direction as R2. How about these two terms? These two terms belong to the acceleration term of the length 3. Length 3, this should be the length AB. This length AB, that length do general motion, so it has two components of the acceleration, one normal, one is tangential. Which one of these two components is the normal? The one with theta dot square, because this should be omega square, so R omega square, this gives us a normal acceleration component, and it is opposite to the R3. It is opposite to the R3, so it means that we have a normal component, a normal, that goes opposite to the R3. Make sense? So there should be a normal vector of this length. How about the A tangential vector? The A tangential should be R alpha, because this is theta 3 double dot. This should be alpha, the angular acceleration, and it should be perpendicular because there is pi over 2. So it should be perpendicular, it should be normal to the length 3 with a 90 degree, and it should go in the same direction as alpha 3, which is alpha AB. Alpha AB, we got it here negative. We got it down here. We got it negative, which indicated that it rotates clockwise direction. So the direction of alpha 3, it should rotate clockwise direction. So if this is the direction for the omega AB, so alpha AB should go opposite to it as alpha AB. It should be the theta 3 double dot. It is clockwise direction. So if this one goes clockwise direction, and the direction of the tangential component, it should be normal and goes in the same direction as alpha AB, so there should be the A tangential vector of the length AB. And that's it. There is no acceleration here for the slider B. Why? This velocity is a constant velocity, uniform velocity. So that's why we have this right term here. The term on the right hand side of this Lagrange equation is already 0. Make sense? So this is how we can set even or define the directions of these different velocity and acceleration analysis and acceleration. And this is generally how we can do kinematic analysis for a mechanism. Make sense? So that's it for this video, and the next video basically we gonna consider more examples on the velocity, position velocity and acceleration analysis, the kinematic analysis of mechanisms using the complex algebraic method, and by then after that we're gonna move directly to the graphical method.